Hi, this is Moe Hasanovic from Indian River State College, and this is lecture 2 in our fiber optics video series. We are talking about important properties of light today. In order to properly understand the theory of fiber optics and light propagation through optical fibers, we have to take a step back and review or learn more about the basics of light, some important properties of light. Light is used as a medium to transfer the information through the optical fibers. So from that aspect, it's very important to understand the way how light generally behaves and what are the important parameters and important quantities or variables that would define the properties of light. So that is basically the topic of today's lecture. Some of you who have a background in photonics may be familiar with some of the concepts that we are going to be covering today. So please use this lecture as a review for others who are new to the field of photonics. This lecture is going to be very useful to build some of the foundations of photonics that are used not only in photonics and fiber optics, but also in other fields of photonics, such as lasers or geometrical optics, etc. There are a few learning outcomes that we need to achieve today. As a result of this lecture, you should be able to understand the nature of light propagation, at least on a basic level. We're going to spend some time discussing the electromagnetic theory of light, and finally, we're going to spend a significant amount of time talking about different properties of light. In the field of fiber optics, we are using light as a medium that carries information along some sort of guiding structure, which in this case is known as optical fiber. So in order to properly understand the behavior of light along an optical fiber, we are going to start this review of the basic properties of light by discussing the propagation of light and some of the important factors that would determine the behavior of light in a specific medium. So there are two basic factors that need to be analyzed and understood. One are the properties of the light, and another one are the properties of the medium. So the medium is a supporting structure, and light is going to be the carrier of the information that is going to travel through that medium. So there is going to be certain interaction between the light as an information carrier on one side and the medium as a supporting structure through which light is going to propagate. So we are going to visit each of these two basic aspects of the light propagation and try to understand how they affect the behavior of light and its information capacity when light carries information either in a free space or specifically in the case of fiber optics as the light propagates along an optical fiber. In order to understand the basic properties of light, we are going to start with the basic question of what is light. This question preoccupied many scientists throughout the history of science, and today, at this level of knowledge, we are looking at light as a form of electromagnetic energy that has both wave and particle properties. It turns out that certain phenomena that are related to the light can be explained only if you're looking at the light as a wave, while some other phenomena can be explained only if we are looking at the light as consisting of many small particles. So for example, when the light travels through the space or passes through small openings, it is going to behave like a wave, similar to like water waves or sound waves to a certain level. So in other words, light is going to behave like as if it's made up of connected electric and magnetic fields that are vibrating and traveling together. On the other side, there are other phenomena that cannot be explained by looking at light as a wave. Certain phenomena such as absorption In other words, the way how the light is interacting with the medium by reducing its power and transferring its energy onto the medium can only be explained if you're looking at the light as a bunch of small particles that are interacting with the particles of the supporting medium. This slide here lists important parameters that are going to be used to describe the properties of light. The most important are the wavelength, the frequency, the period, the amplitude, the speed of light, the phase, and also the coherence, the polarization, and finally the energy of light. On the slides that follow, we are going to discuss each of these parameters individually, and we are going to try to properly understand them, as they play a very important role in the field of photonics and also in the field of fiber optics. So let us first talk a little bit about the wavelength. We have already mentioned that light behaves as an electromagnetic wave. What do we mean by wave? What is a wave? How can we define a wave? A simple explanation is that you can look at a wave as some sort of disturbance that takes place, that occurs both in the space and in the time. So for example, if you're looking at the water waves, if you look at the waves on the ocean, you are going to look at the disturbance, you're going to look at the peaks and valleys that are distributed along the space. In other words, at different locations, you're going to have a peak or a crest, and at some other locations you are going to have a valley or the minimum. Similar disturbance, similar vibration also occurs in time. So for example, if you are anchored in a boat at the same location, over time that boat's going to be moving up and down. So at certain points in time you're going to be at a peak or at the crest, and then at some other time you're going to be moving down into the valley or at a minimum position. So that's what we consider a wave. In order for a wave to be a wave, there has to be a disturbance both in space and in time. And that disturbance can be a disturbance of different types of quantity. If we are looking at the ocean wave, we are talking about disturbance of water. If we are looking at a sound wave, then we are talking about disturbance of air molecules. In this specific case of light, we are talking about an electromagnetic wave. We are talking about a disturbance of so-called electric field and a magnetic field. You can, to a certain extent, correlate electric field to the voltage and magnetic field to the current. So if you're looking at a light as an electromagnetic wave, we are talking about a disturbance of the current and the voltage in space and in time. So in order to properly describe that disturbance, that change from a minimum to a maximum in space and in time, we are going to use different parameters to describe those. One of the parameters is a wavelength. So what you see here on this slide, on the bottom is some sort of wavy, or if you want to be more specific, sinusoidal curve, where you can notice a whole bunch of peaks, positive peaks or crests, and also a series of negative peaks. The wavelength is defined as the distance in space between the two neighboring crests, between the two neighboring peaks. So if you're measuring the distance in space, we said that a wave is a disturbance in space in addition to being a disturbance in time. So in this case here, we are considering disturbance over the space. That's why along the x-axis we are using a parameter of distance. So if you're measuring the distance in space between the two crests or the two peaks, that distance is so-called wavelength. That's how we are defining the wavelength. So the wavelength represents, again, the distance over which the wave repeats itself, distance in space. We are using the Greek letter lambda to describe the wavelength, and obviously the units that are going to be used to describe the wavelength are going to be units of distance, be it meters or smaller units such as micrometers, in the case of light nanometers. Of course, you all can also use British units. You can use inches or mils, etc. So again, the wavelength represents the parameter that describes the distance in space between the two crests or two peaks or two maxima in some sort of wave. In this case, light as an electromagnetic wave. We have already elaborated the wave behavior of light, and we also define the wave as a disturbance of a certain quantity, both in space and in time. On the previous slide, we were focusing on the disturbance in space, and we defined the wavelength as the distance in space between the two peaks or the two maxima of a wave. On this specific slide, we are shifting the gears to time domain. In other words, we are talking about the disturbance or vibration in time. So we are still dealing with a similar wavy or sinusoidal curve, but the fundamental difference here is that along the x-axis we are representing the time as opposed to the space or the distance that we had on the previous slide. So what we can observe here is that over time the value of a certain quantity, in this case electromagnetic field, is going to be changing from the positive peak to the negative peak to the positive peak to the negative peak, etc. So we are having a disturbance or vibration of a electromagnetic field over time, and the parameter that is going to describe this behavior in time, this oscillation in time, is going to be the period. So the period is basically the distance in time between the two peaks. In other words, if we are measuring how much it takes to go from one positive peak to the next positive peak, that duration is going to be defined as a period. The number of cycles or number of the peaks that occur within 1 second is so-called frequency. So there is a certain correlation between the period and the frequency. The period represents the interval of time over which the wave repeats itself, while the frequency represents the number of cycles of the wave in 1 second. We are using the Greek letter nu, or very often a letter f, to represent the quantity of frequency. At this point, we are also going to introduce another very important parameter that describes the light, and that is the speed of light. So light propagates through a specific medium at a certain speed. It turns out that the speed of light is a constant in a specific medium. So if you're looking at a vacuum or air, then the speed of light is going to be equal to 3 times 10 to the 8 meters per second. So that is a constant that is going to be very frequently used in photonics, and it's to be remembered. So again, the speed of light in a vacuum is a constant that is equal to 3 times 10 to the 8 meters per second, or 300 million meters per second. Let us summarize what we covered so far. We have defined a wave as a certain disturbance that takes place both in time and in space. In order to properly describe the properties of a wave, we are introducing two parameters. We have introduced the wavelength that would properly describe the disturbance in space. In other words, the wavelength is going to be the distance between the two peaks in a wave, and in order to properly describe disturbance in time, we have introduced the period as an interval in time to complete one full cycle. We have also mentioned that the light represents an electromagnetic wave. In other words, in the case of light, electric field and magnetic field are vibrating or oscillating in space and time. Let us now focus our attention to another important parameter of light, and that's the speed of light. On the previous slides, we talked about the speed of light being a constant, and being equal to 300 million meters per second in air or vacuum. It's also important to mention here that the light travels in straight lines, similar to any kind of other electromagnetic signal. So light pretty much behaves in a similar way as an electromagnetic signal that is being used to transfer information from your cell phone or smartphone to the tower. It's just that the frequency or the wavelength of those two types of electromagnetic waves is going to be the different. So again, the speed of light is approximately equal to 3 times 10 to the 8 meters per second, or 300 millions of meters per second, or if you wish, it is actually equal to 186,000 miles per second. It's important to mention that this is only in a free space, either in air or vacuum, and that the speed of light is going to change if the light moves from one medium into another. So the speed of light depends upon the medium through which the light passes. The highest speed is the speed of light in air or in the vacuum, and we are going to see on slides that follow that light is going to actually reduce its speed if it passes from air or vacuum into some other medium such as water or glass, etc. So this is very important to understand, because it's going to have certain profound effects in fiber optics, since we are using glass as a material to make the core of an optical fiber that is going to be used as a light guiding region through which the light is going to propagate and carry information from one side to the other side, from the transmitter to a receiver. Here we have a very clear comparison between 3 waves at 3 different frequencies. We are seeing a wave at frequency of 4 Hertz on the top, and then we have a wave whose frequency is 2 Hertz in the middle, and finally the wave whose frequency is 1 Hertz on the bottom. So again, the frequency is basically equal to the number of cycles completed within 1 second. So 4 Hertz means that 4 cycles are completed within 1 second. 2 Hertz means that 2 cycles are completed within 1 second. And finally, 1 Hertz is the meaning of 1 Hertz is that 1 cycle is completed within 1 second, which is clearly shown on this slide. This slide in the bottom right corner also gives you 2 important formulas that are to be remembered that very clearly establish the correlation between the 3 parameters that we have introduced so far: wavelength, the frequency, and the speed of light. It's important to mention that these formulas at this point, the way how they have been written, can be applied only for air or vacuum. So wavelength, we are using the letter lambda. The speed of light, we're using a small letter c, and finally the frequency, we're using the Greek letter nu. So there is a correlation between these 3 in the sense that, for example, the first formula on the top basically is stating that the wavelength of light in a vacuum or air is equal to the ratio of the speed of light c and the frequency of that wave or that light nu. This slide dives a little deeper into the whole aspect of an electromagnetic wave. We have already described the light as an electromagnetic wave, and we said that an electromagnetic wave is a wave where disturbance occurs in space and time, and the quantity that vibrates or disturbs is electric field and magnetic field. Again, electric field can be looked at as voltage, and magnetic field can be looked at as a current. On the bottom of this slide, we have a 3-dimensional representation of an electromagnetic wave. We said that an electromagnetic wave consists of an electric field and a magnetic field. Electric field here is shown in orange color, and it's shown here as oscillating vertically, to form so-called electric wave, and then the magnetic field is shown here in a purple color, and it's shown here as oscillating horizontally to form a magnetic wave. So these two quantities, electric field and magnetic field, are perpendicular to each other. They're at right angle relative to each other. What we described here is so-called transverse wave. It turns out that there are different types of waves. They are so-called longitudinal waves, and there's also so-called transverse waves. What do we mean by transverse wave? If you're looking at these two quantities that describe electromagnetic wave, namely electric field and magnetic field, they are perpendicular to each other, and they are also perpendicular to the direction of the propagation. That's an important property of a so-called transverse wave. So the oscillation is basically taking place in a plane that is perpendicular to the direction of propagation. In the case of an electric field, we see that oscillation is taking place in a vertical direction, right? And then the oscillation of the magnetic field is taking place in a horizontal direction, and those two directions are perpendicular to the axis of the propagation. In the case of longitudinal waves on the other side, we'll see that the disturbance or oscillation is going to be basically taking place along the direction of the propagation. So that is a fundamental difference between a transverse wave and a longitudinal wave. Here we can see a short demo of an electromagnetic wave where yellow arrows represent the electric field and the blue arrows represent the magnetic field. We see that the yellow arrows are oscillating in a vertical direction. The blue arrows are oscillating in a horizontal direction, and both yellow and the blue arrows are perpendicular to the direction of the propagation of this wave that happens to be in the direction of the x-axis, as shown here. So once more, let's repeat this demo to see how an electromagnetic wave looks in space and time. To further explain the idea of transverse waves, here we are using an analogy with the waves in the water. So a simple example of a motion similar to the transverse radiation waves can be made by dropping a pebble into a pool of water. So if we drop a pebble into a pool of water, we are going to create the water waves. So the water is going to be oscillating or vibrating, but that vibration is going to be taking place in an up and down direction, while the wave is going to be traveling in an outward motion, from the center from the source of the wave, which is where the pebble got dropped into the water. So the up-down motion is a transverse type of wave, where we have, as I said, motion of the water up and down, while the water wave that's being created by dropping the pebble is moving outwards on the surface of the water. So the transverse waves spread out in expanding circles until they reach the edge of the pool in much the same manner as the transverse wave of light spread from the sun. However, the waves in the pool are very slow and clumsy in comparison with light, which travels approximately at 300 million meters per second. So there is a certain analogy, but we also have to clearly point out a difference in terms of the speed of the transverse wave that's created in a pool of water by dropping the pebble is the speed is much lower compared to the speed of a light as a transverse wave that's propagating in a free space, from some sort of light source such as sun or any kind of other man-made type of light source, be it a light bulb or a laser or LED, etc. By introducing the concept of transverse waves and in general by looking at the light as a wave, we are slowly introducing the basics of geometrical optics. In order to further expand the concept, we have to define a few other parameters that are important in the description of a light wave. So if we draw lines from a light source, in this case, we're looking at a candle. You can also look at our case with a pebble and a wave that's created in a pool of water. So we see that the candle here as a source of a light is going to be spreading light in an outward direction in exactly the same way the pebble created the wave in the water. So if we focus our attention to the geometrical shape of the waves that have been created, these waves obviously have crests or peaks and also the valleys. If we connect all the points on one crest, we are creating something that's called a wavefront. So in other words, the wavefront is a surface or line in the path of wave motion on which the disturbances at every point have the same phase. They're being either at the peak or at the valley, or at the maximum or at the minimum. We can also create the lines that are drawn from the light source to any point on one of the transverse waves. And these lines indicate direction that the wavefronts are moving, or the waves are moving, and those lines are so-called the light rays. So what we see here as a blue circles will be the so-called wavefronts that are created by connecting the points along the same crest of the wave, and then these rays that are pointing outwards are basically showing the direction of the propagation of this wave. In this case, a light wave, or in the case of our example with a pool of water with a pebble, we can also create certain rays that would show the direction of propagation of the water wave. So wavefront in the immediate vicinity of the light source is a spherical. So if you're looking at this candle here in its immediate vicinity, we have the blue the lines that are in the shape of circles. So we're talking about the spherical wavefronts. As we're moving further away from the light source, from the candle, we see that the radius of each circle is expanding, so they're kind of slowly straightening. So if you're looking at some point at a far distance, you're going to have a very large circle. So the curvature of the circle is going to be much less than the curvature of the circles that are in immediate vicinity of the candle or source of the wave. That's why we are saying that the wavefront is going to turn from a spherical wavefront in a close proximity to the source of the wave into some sort of planar wavefront, where the wavefront is going to be more established along some sort of straight line. So the crest of the wave will not be on a spherical, on a circular line, but it's going to be rather on some sort of straight or planar line. Now that we introduced the important parameters that would describe the behavior of light, such as wavelength, period, frequency, the speed of light, let's focus our attention to the behavior of light, or when it is propagating in some sort of medium. In other words, let's talk a little bit about how the light interacts with the medium in which it propagates. There's a few important phenomena that are immediately coming to our attention when we're talking about the interaction of light with the medium. And the four phenomena are shown on this slide, namely reflection, absorption, refraction, and transmission. So on the right side of this slide, we see each of these four important phenomena that are related to the interaction of light as it is moving through a medium or passing from one medium into the other medium, etc. So when light waves travel in straight line, encounter any substance, they're either reflected, absorbed, transmitted, or refracted. So what each of these terms mean? So reflection is similar to the reflection of any other wave. So if you have like water wave, wave in the ocean that's hitting some sort of obstacle, some sort of wall, that wave is going to be reflected. So in a similar way, the light is going to also behave when it hits some sort of boundary between the two media. We can observe this behavior in many cases in the real life. The way how we see ourselves in the mirror is exactly due to the reflection of light that creates the mirror image of us, and by means of that reflection we can see ourselves in the mirror. The refraction is the way how the light interacts with the two media as it's passing from one medium into the other medium. We'll see that the light is moving along the straight line. However, it is going to bend as it is passing from one medium into the other medium. It's going to bend either towards the axis or away from the axis that's been established perpendicular to the surface or to the boundary between the two media. Absorption is yet another phenomenon that is related to the reduction of the power or the strength of the light. If as light is moving through a certain medium, it is going to interact with the molecules of that medium, in a sense that the energy that a light carries is going to be transferred to a certain extent to the molecules of the material, and an immediate macroscopic consequence of that is that the light is going to get dimmer as it is moving to a certain material. So that's going to result in a certain loss of power. This is a very important concept to understand, especially from the aspect of fiber optics, because we are going to be moving the light through an optical fiber, and optical fiber is made out of glass, so there is going to be a certain interaction between the light and optical fiber and the glass, in the sense that we're going to be losing the power, and that's going to have an immediate consequence on how far we can send a light signal through the optical fiber without losing any kind of information. We can classify different materials, different substances based on how they interact with the light. Substances that would enable transmission of almost all the light waves are so-called transparent substances, transparent materials. For example, the glass would be most of time a transparent material. We can look at the transparent material also as a so-called see-through material. So if we can see through a certain material on the other side of the material, it means that the light is passing through that material. There is no substance that's perfectly transparent, but many substances are very nearly transparent. In other words, there is no absorption the absorption that's happening inside of that material is reduced to really very, very low levels. In addition to transparent materials, there is also other two important categories of materials based on the way how they interact with light, namely translucent and opaque materials. So the materials through which some light rays can pass, but through which objects cannot be seen clearly because the rays are diffused, are so-called translucent materials. So those materials would be, for example, the frosted glass of a light bulb, or a piece of oiled paper would be examples of translucent materials. The materials that are unable to transmit any light are so-called opaque materials. So opaque materials would either reflect or absorb all the light rays that fall upon them. All substances that are not light sources are visible only because they reflect all or some part of the light reaching them from some light source. If light is neither transmitted nor reflected, it is absorbed or taken up by the medium. In other words, the energy of the light is being absorbed, it's being sucked up by the molecules of that material. When the light strikes a substance or material, some absorption and some reflection always would take place, will always occur. In other words, no substance is completely transmittable, or in other words, there is no material that completely transmits or reflects or absorbs all the light rays. but there are certain materials that are nearly transparent. In other words, they very nearly transmit all the lights. There are also certain materials that are very good reflectors. In other words, they are reflecting a very high percentage of light that's hitting those types of materials, etc. So again, the materials in general can be classified in three main groups, so-called transparent materials, translucent materials, and opaque materials. And this categorization is based on how the materials interact with the light as the light is hitting or passing through that type of material. As you have probably noticed, we have switched our discussion from the properties of light to the properties of the materials through which the light is propagating. At the beginning of this lecture, we established the criteria of what we are going to discuss in this lecture. We said that we're going to be focusing on two main factors. One is the properties of light, and another are the properties of the materials through which light propagates. So we have started talking about this second main factor, and that those would be the properties of the materials. So we have already categorized different materials into three main groups based on how they interact with light. We also want to establish certain parameters or certain quantities that are going to be used to describe the properties, the optical properties of the material. The most important parameter that is to be introduced and discussed is so-called index of refraction. Index of refraction is the main parameter that is going to describe the optical properties of the material that is relevant to the propagation of light, and also from the aspect of fiber optics, that's the most relevant to the optical fibers. So how do we define this parameter? How do we define the index of refraction? Index of refraction is measuring the speed of light in an optical medium. We already discussed about the speed of light in air or vacuum, and we established a constant 300 million meters per second as being the speed of light in air or vacuum. It turns out that when the light propagates through a medium different than air or vacuum, the speed of light is going to be reduced below 300 million meters per second. The amount of how much the speed of light is reduced in a specific medium, in a specific material, is given by so-called index of refraction. So the index of refraction of a material would be the ratio of the speed of light in a vacuum to the speed of light in that specific material. So the speed of light in the free space or vacuum is equal to 3 times 10 to the 8 meters per second. When the light enters the material, that's some sort of optically dense medium, the speed of light is gonna be reduced, or the light is gonna travel slower at some sort of speed v. So the ratio between the speed of light in air, shown here in a small letter c, and the speed of light in that specific medium that's shown here with the small letter v, that ratio is going to be equal to the index of refraction as shown in this formula here in the box. We have already introduced a few specific phenomena that describe the interaction of the light with the medium, with the supporting medium. One of the phenomena was the reflection. This slide here established a certain law that's going to define how the light is going to behave as it reflects from a certain surface or from a certain medium. According to the law of refraction, the angle of incidence is equal to the angle of reflection. What do we mean by angle of incidence or angle of reflection? On this slide here on the bottom, you see the incident wave. That will be the wave that's coming from a certain direction, and it's going to hit a surface or a boundary between the two media. So we have a medium above the surface, and we also have the medium below the surface that's shown here in the green color. So the incident wave, as it's propagating, is going to hit the boundary between the two media, and then it's going to get reflected, and it's going to turn into a reflected wave that is shown here in the blue color. So if we establish the axis that's perpendicular to the boundary between the two media at the point where the incident wave hit the boundary, and then we measure the angle between that axis and the incident wave. That angle is going to be called angle of incidence. Similar to the angle of incidence, we can also establish the angle of reflection. That is going to be the angle that's made by the again by the axis perpendicular to the boundary and the direction of the reflected wave. These two angles are always equal to each other according to the law of reflection. Refraction of light is described through so-called Snell's law of refraction. So on this slide here, we see on the bottom right corner a case where a light is coming from the direction A in a medium above the surface, medium that's described by the index of refraction N1, and it's going to hit the boundary between the two media at the point B. So as the light is traveling in the first medium, in the above medium, in this case in air, it's gonna propagate along the straight line from the point A to the point B. At point B, it's gonna hit the boundary between the two media, and it's gonna pass into the second medium, into the glass. And while it's passing, it's gonna change its direction. In other words, it's going to bend. It's gonna change the direction of the propagation. So the straight is still going to propagate along the straight line, but that straight line in the second medium will not be the same straight line as the straight line in the first medium. So from the point B to the point C, we have another straight line as opposed to the straight line between the point A and the point B. So how do we establish the amount of the bending? How much the light is going to bend as it is moving from one medium into the other? There's a mathematical formula that's shown here on the top of this slide that establishes the correlation between the properties of the two media, index of refraction N1 of the first medium, index of refraction of the second medium N2, and the two angles, the angle of incidence and the angle of refraction. Again, similar to the definition of the angle of incidence and the angle of reflection established on the previous slide, we can define the angle of incidence and angle of refraction. We are going to create the axis that's perpendicular to the boundary that's passing to the point B where the light hit the surface. That axis is shown here as a red line. And then we are going to establish two angles. One angle is going to be the angle between the light ray coming from the first medium and the axis. That's going to be called the angle of incidence. And then on the bottom medium, where the light refracted into, we are going to have the angle of refraction, which is going to be made again by the perpendicular axis shown in the red color here, and the line of propagation of the refracted wave that's moving from the point B to the point C. So these two angles, alpha and beta are also showing up in the equation on the top of the slide. So there's a clear correlation between the angles of incidence and the refraction and optical properties of the two media N1 and N2 that is shown in the equation above. We are going to introduce another important phenomenon that's related to the behavior of light, so-called diffusion. So if we are talking about some sort of a medium, like two different types of materials, where one material has a very rough surface, when the light hits that rough surface, it's gonna get reflected in many different directions. In such a case, we are talking about scattered or diffused beam of light. So the diffusion of light or scattering of light is occurring if the boundary between the two media is not smooth. In other words, it has a certain roughness that's going to create the reflection or scattering in many different directions. What we see on this particular specific slide, the incident light is shown in a blue color, and then the reflected or diffused light is in many different directions due to the fact that the surface from which the light is reflected has a certain roughness. And finally, let's also revisit the topic of absorption of light. We already talked about the absorption as the phenomenon of transferring energy of light into the medium through which the light propagates. An immediate consequence of that is that when the light travels or propagates through that medium, it's going to get dimmer. It's going to lose on its power. There's a few other things that are important to be mentioned when we're talking about the absorption of light. Absorption of light is actually responsible for us, our ability to see different colors. So if the light beam falls onto a piece of a black paper, the black paper is going to absorb most of the light rays, and very little light is going to get reflected from the paper into our eye. That's how we are getting a feeling of a black color. If we have some other surface, for example, in this case here, on this slide, you can see bananas. Obviously, bananas are yellow, so how do we explain why we are seeing bananas as being yellow and not as being blue or red? So it turns out that when the white light hits the certain boundary, white light consists of all the colors of the spectrum, from the red all the way to the purple. So a certain surface, in this case a surface of a banana, is going to absorb all the colors of the light but the yellow. The only yellow color is going to get reflected, it's going to come into our eye, and that's how we are going to perceive bananas to be yellow. This is just another example of an absorption of light that plays an important role in our life. As a summary to this lecture, we discussed about the important properties of light today. We are establishing foundations to discuss the behavior of light in an optical fiber. We have discussed on a top level about two basic factors that would affect the behavior of light as it propagates in a certain medium. One is the properties or the nature of light, and on the other side is the properties of the medium. We have established a whole bunch of different parameters that are used to describe the light. We have talked about the wavelength, we have talked about the period, about the frequency, and finally speed of light. We define the light as an electromagnetic wave, and also we used another theory that describes the light as a whole bunch of small particles that are interacting with the medium. As far as the materials and their impact on the light propagation, we have categorized the materials into three main groups: transparent materials, translucent materials, and opaque materials. We have also discussed what kind of parameters are used to describe the optical properties of the material. We have introduced the index of refraction as the most important parameter. And finally, at the end of the lecture, we have talked about the reflection, refraction, absorption, and diffusion of light. Each of these different phenomena are related to the interaction of light in a medium that is used to support the propagation of light. Each of these different phenomena, reflection, refraction, absorption, is briefly described. Certain laws have been established as to how a light reflects or refracts from a certain boundary between the two media, and those would be the basic foundations of the theory of light and photonics that are going to be important to understand how the light is going to behave inside of an optical fiber. Next time in lecture 3, we are going to be focusing on that specific aspect of the light propagation along the optical fiber. A lot of foundations that we established in this lecture that are related to the behavior of light is going to be also applicable to the propagation of light along the optical fiber. We'll see that, for example, refraction is going to play an important role in how the light is bouncing back and forth inside an optical fiber. We also see that absorption also plays an important role from the aspect of the power loss, and we're going to establish a certain correlation between the absorption on one side as a main cause to the loss of the signal in the optical fiber, and we're going to establish a certain limitations in terms of how far we can transmit light inside of an optical fiber from a point A to point B. That is going to be based on the amount of loss that's going to be present inside the light guiding region of an optical fiber due to the absorption. So spend some time reviewing the material that we covered today to establish the foundations. If you are new to the field of photonics, some of the parameters and concepts that we described today is going to again play an important role in the way how we're going to treat optical fibers, and without having these foundations that are presented in this lecture, it's going to be very difficult to understand how light behaves in optical fiber. So start building your knowledge with this and the previous lecture so that you gain a better understanding of the theory of fiber optics. With this being said, I hope you enjoyed this lecture and you learned something new, and I'm looking forward to see you next time and continue our journey towards better understanding of fiber optics.